when you break your arm, the X-ray's pretty much binary. I mean, the jagged white line is either there or it isn't.
Right. It's obvious.
Yeah. But today we are diving into the invisible, sort of chaotic chemical battles happening in the air around us,
Yeah.
right? And things they're far from binary.
Absolutely.
So we're using Julia Burge's textbook,
Mhm.
Chemistry, Atoms First, as our survival guide today. And this particular deep dive is actually engineered for a very specific listener.
Mhm.
You are a community college chemistry professor out in Oregon, right? You're prepping for your 3-term sequence, fall, winter, spring. And your mission today is to figure out the absolute best way to translate this incredibly dense material for your students.
Which is, I mean, arguably the most critical job in science education right now.
Right.
Yeah, because community college general chemistry, that's the proving ground. If a student doesn't grasp the underlying physical why during these first few terms, the really heavy calculations they face later on.
It's just going to feel like math for the sake of math.
Exactly.
Yeah.
It'll just feel like arbitrary punishment.
So our goal today is to extract the most effective teaching strategies from this material. We want to identify the common roadblocks your students are going to face, find those really sticky analogies that make abstract concepts just sort of snap into focus.
Right.
And we really want to look at how Earth's atmosphere serves as basically the ultimate laboratory for molecular behavior.
And honestly, the Atoms First approach that you're using is actually perfect for this.
You think so?
Oh, yeah.
Yeah.
It forces us to start with the fundamental, quantum behavior of individual elements before we even try to understand these massive macroscopic phenomena.
Like global weather patterns or smog.
Right, exactly. You build from the atom up.
Okay, well, let's put that approach to the test then. Instead of just walking through the textbook chronologically, let's look at how energy interacts with matter, starting with, the most extreme example.
good.
So, way high up in the outer layers of the atmosphere, the thermosphere Earth's chemistry is basically constantly being bombarded by the sheer violence of outer space, right? Like, solar flares are ejecting massive streams of these high-energy electrons and protons.
And Earth's magnetic field actually funnels those streams toward the poles.
Mhm.
And that's where they slam into the really sparse oxygen and nitrogen molecules in our upper atmosphere.
Okay.
So that collision, it transfers just an enormous amount of energy,
Yeah.
kicking those atmospheric atoms into what we call an electronically excited state.
Right, but my assumption, just reading the text, is that physics hates an excited state. Like, everything wants to return to a baseline, right?
You're exactly right. Nature always, always seeks the lowest possible energy state. So those electrons, they can't maintain that higher orbital indefinitely.
Right.
They drop back down to their ground state. But that excess energy, it has to go somewhere. So it gets emitted as a photon of light.
Oh.
And this is the physical mechanism behind the northern and southern lights of the auroras.
Okay, but the textbook mentions very specific colors, right? Green, red, blue, violet.
Mm-hmm.
Why isn't it just a chaotic wash of white light? I mean, if I'm a student sitting in your class, I'm probably picturing a light bulb turning on, which gives off a continuous spectrum.
And see, that is a fantastic pedagogical moment for your classroom right there.
Yeah.
This is where you can really cement atomic theory for them. The colors aren't random because the electron orbitals are quantized.
Quantized, meaning specific steps.
Exactly. So an oxygen atom dropping from one specific excited state to a lower state, it releases a photon with a very, very specific energy. And our eyes perceive that exact energy as a brilliant green.
Oh, wow.
Yeah. And a different energy drop in nitrogen yields blue.
Yeah.
So it's essentially a giant atmospheric emission spectrum happening in the sky.
So you can literally point to the sky and say to your students, hey, that green color is the physical proof that electron orbitals exist at discrete energy levels.
You absolutely can.
I love that. I mean, that's such a great hook. But the auroras aren't the only glowing phenomena up there, right? The text brings up something called the mystery glow of space shuttles, which astronauts saw back in 1983.
Oh, yeah, this is a fascinating one.
They saw this eerie orange glow on the exterior of the spacecraft. But wait, isn't the gas up in the thermosphere incredibly thin?
It is extremely sparse.
So how are enough molecules colliding to create a visible glow? Like, it doesn't make sense.
And see, that intuition, that's exactly what trips up a lot of students. They tend to visualize gas phase reactions as molecules just aimlessly bumping into each other in this giant empty void.
Right, like ping pong balls in a huge room.
Exactly. But you introduce a solid surface into that void, and the entire dynamic changes. The silica tiles on the space shuttle's exterior, They actually provided a surface for absorption.
Absorption, with a D, meaning the molecules were actually sticking to the ship.
They were adhering right to the surface, yes. Specifically, nitric oxide molecules were absorbed onto those tiles. Now remember, the shuttle is moving at orbital velocity.
Which is insanely fast.
Very fast. It's sweeping through that thin atmosphere, meaning fast-moving oxygen atoms are just slamming into that nitric oxide. The surface basically acts as an anvil.
Oh, so.
It holds the nitric oxide in place, which dramatically lowers the activation energy required for the collision to actually form excited nitrogen dioxide.
And then, just like the auroras, that excited nitrogen dioxide drops back to its ground state and emits a photon.
You got it. Specifically an orange photon. And they actually proved this intentionally later on in 1991 aboard the Shuttle Discovery.
Wait, how do you prove that?
Well, they released various inert gases, like neon and xenon, into the shuttle's wake, and nothing happened. But when they vented nitric oxide, the orange glow intensified dramatically.
That is so cool.
That is, it's this brilliant, tangible example of surface chemistry operating in basically a near vacuum.
Okay, so we've seen what high-energy charged particles do at the very edge of the atmosphere. But light from the sun isn't just particles, right? It's also high-energy electromagnetic waves, like ultraviolet radiation. And to understand how the Earth handles that, we really have to look deeper down into the atmosphere at the stratosphere.
The home of the ozone layer.
Right. So the text explains that ozone, O3, acts as a shield, absorbing UV light that would otherwise cause, severe genetic mutations and skin cancer down on the surface.
Exactly.
But we nearly destroyed it with chlorofluorocarbons, or CFCs. And Sherwood Rowland and Mario Molina actually won the Nobel Prize for figuring this out. But here's my question, and I bet your students will ask this too.
Okay, lay it on me.
Down on the surface, CFCs were used as coolant specifically because they were incredibly heavy and utterly unreactive.
Right, they're super stable.
So how does a heavy, completely unreactive gas even reach the stratosphere? Wouldn't it just sink?
And that is a classic student misconception right there. People often assume that the atmosphere is perfectly stratified by weight, like oil and water in a glass.
Right, heavy stuff at the bottom, light stuff at the top.
Exactly. But the troposphere, the layer we live in, is incredibly turbulent. Over a timeline of years and decades, constant weather patterns and atmospheric mixing will slowly diffuse even heavy, stable gases upward.
Wow, okay.
And honestly, their very stability is exactly what allowed them to survive that long journey.
Because they don't react with anything along the way, they just sort of grift upwards, totally inert, until they cross into the stratosphere.
Exactly. But once they hit that altitude, they're no longer protected by the ozone layer because they're above the bulk of it.
Oh, no.
Yeah. So the high-energy UV radiation from the sun is finally strong enough to just break the carbon-chlorine bond in the CFC molecule,
leaving us with a free chlorine atom. Now, I've heard this free chlorine described in pop science as like a biochemical serial killer, but that doesn't feel scientifically accurate, right? Because we aren't talking about biology here, it's just atmospheric chemistry.
Yeah, I'd probably avoid that term in a chemistry class.
So how should a professor frame this for their class?
I would suggest framing it mechanically. You want to focus on the difference between a reactant and a catalyst. Because a reactant is consumed in a chemical process, right?
Right, it gets used up.
Exactly. If chlorine were just a reactant, one chlorine atom would destroy one ozone molecule, form a stable bond, and the problem would be contained.
It would be a one-to-one trait.
Right. But chlorine acts as a catalyst.
Ah, like a master key that keeps unlocking doors but never gets stuck in the lock?
That is a perfect analogy, actually. Use that.
Yeah.
The chlorine atom steals an oxygen from the O3, which creates chlorine monoxide and normal O2 gas.
Okay, that makes sense.
But then, that chlorine monoxide bumps into a free oxygen atom floating around, which rips the oxygen away from the chlorine.
Which releases the chlorine atom again.
Exactly. It's released to start the process all over again. So a single chlorine atom can catalyze the destruction of up to 100,000 ozone molecules before it finally forms a stable compound and settles out of the stratosphere.
Wait, 100,000 to 1.
Yeah.
That is a brutal ratio. Just
Yeah.
brutal. And I guess this brings us to the famous Antarctic ozone hole, which always confused me. Why Antarctica? I mean, most of the CFCs were released in the northern hemisphere by, industrialized nations.
Right. Mostly North America and Europe.
So why did the catastrophic damage happen over the most remote, completely unpopulated continent on Earth?
Well, it actually circles right back to the concept we just discussed with the space shuttle. Surface chemistry.
Really? Down in Antarctica?
Yeah, because The Antarctic winter is uniquely harsh. There's a massive weather system called the polar vortex that isolates the air over the pole, dropping temperatures so incredibly low that polar stratospheric clouds form.
Okay.
And these aren't regular rain clouds. They're made of tiny, solid ice crystals.
Oh, so the ice is providing a physical surface, just like the silica tiles on the shuttle.
You're putting it together perfectly. And those ice surfaces act as a sponge for relatively stable chlorine compounds that had actually stopped reacting.
Okay.
The ice hoards molecules like hydrogen chloride, providing a sort of staging ground for them to react and form molecular chlorine gas, CO2. And this gas just builds up in the dark, cold vortex all winter long.
Just waiting. And then the moment the sun rises in the spring,
Boom. The sudden influx of UV light shatters all that built-up molecular chlorine, releasing millions of highly reactive atomic chlorine atoms simultaneously.
wow.
That sudden, massive spike in catalytic activity creates the huge, localized depletion we call the ozone hole.
It's just amazing how it all connects. Okay, so ozone handles the high-frequency, dangerous UV waves coming in, but the Earth absorbs all that sunlight and then radiates thermal energy back out into space as, lower frequency infrared radiation. Right, so now we need to talk about trapping that heat in the troposphere.
The mechanics of greenhouse gases.
Yes. And here is where my hypothetical students, and honestly probably some real ones, get really confused. The atmosphere is about 78% nitrogen and 21% oxygen.
Correct.
Yet the text notes that carbon dioxide, which recently crossed, the 400 parts per million mark?
Yeah, just over 400 ppm now.
Right. It notes that CO2 is somehow driving the global temperature. How can a tiny trace of gas, literally parts per million, control the temperature, while the gases making up 99% of the air do absolutely nothing?
That is a very common question, and answering it requires shifting the student's focus from atomic theory to molecular geometry.
Okay, how so?
Well, we tend to draw molecules on a whiteboard as static balls connected by rigid sticks, right?
Yeah, the classic ball and stick model.
Right, but in reality, those bonds are incredibly dynamic. They vibrate, they stretch, they bend like springs.
So the molecules are constantly jiggling around.
They are. But the specific way they jiggle determines their interaction with heat. Remember, the Earth is radiating infrared energy. To absorb that specific frequency of electromagnetic wave, a molecule must be what we term IR active.
IR active, meaning what exactly?
It means its dipole moment, which is the physical distribution of its electrical charge, must actually change during the vibration.
Okay, let's apply that. Let's look at nitrogen and oxygen, the 99%.
Sure. Nitrogen and oxygen are homonuclear diatomic molecule. Two identical atoms.
Right. N2 and O2.
So they are perfectly symmetrical.
Mm.
When they stretch or compress like a spring, the electrical charge remains perfectly balanced between the two identical atoms.
I see.
Because the charge doesn't shift back and forth, it cannot interact with the alternating electric field of an infrared photon. The heat radiates straight through them as if they are completely invisible.
But CO2 is built differently. It's a carbon atom in the center with an oxygen on each side.
Exactly.
Yeah.
And because of that specific structure, carbon dioxide can vibrate asymmetrically. One side stretches while the other compresses, or the entire molecule bends in the middle like a boomerang.
Okay.
And as it undergoes these asymmetrical movements, the center of its electrical charge rapidly shifts back and forth.
So it's essentially dancing, and that shifting charge is what catches the infrared wave.
Exactly. The physical oscillation of the charge matches the frequency of the infrared radiation. That allows the molecule to absorb the photon's energy, which traps the heat in the lower atmosphere. Water vapor operates on a really similar principle.
That is a phenomenal visual for a lecture. The overwhelming majority of the atmosphere is just standing still on the dance floor, completely ignoring the music. That's wild. Okay, so we're talking about trapping heat, but human activity also traps toxic byproducts. The chemical reactions from industry and transportation create this localized soup in the troposphere.
Yeah, unfortunately.
Let's look at acid rain. The text identifies sulfur dioxide, SO2, as the primary culprit, originating from impurities in coal. It oxidizes and reacts with water to form sulfuric acid.
And addressing that at a regulatory level actually led to some fascinating applied chemistry. Because instead of trying to, filter the entire sky, engineers targeted the power plant furnace itself using powdered limestone, which is calcium carbonate.
But why limestone? I mean, my students are going to ask, what is the actual mechanism making that work?
It relies on thermal decomposition and a really clever phase change. Inside the extreme heat of the furnace, the solid calcium carbonate decomposes into carbon dioxide gas and solid quicklime, or calcium oxide.
Okay.
And that solid quicklime is highly reactive, so it immediately binds with gaseous sulfur dioxide.
Forming solid calcium sulfite.
Exactly. Which can literally be physically swept out of the furnace before it ever reaches the smokestack.
Wow. That is like a fundamental cheat code for environmental cleanup. You take a dangerous gas, force it to react with a mineral, and trap it in a solid matrix that you can basically just sweep up with a broom.
Yeah, it's so much easier to manage solid waste than gaseous pollution.
Right, obviously. But unfortunately, the pollutants created by automobile exhaust aren't so easily trapped at the source, right? Which leads us to photochemical smog.
Right, smog is a whole different beast.
Because cars don't just burn gasoline, they suck in the surrounding air. And inside a car engine, the temperatures get so intense that they force the otherwise completely unreactive nitrogen and oxygen in the air to combine into nitric oxide.
And once that nitric oxide leaves the tailpipe, it hits the cooler air outside and immediately oxidizes into nitrogen dioxide.
And here's where the sun gets involved yet again. Sunlight breaks down that nitrogen dioxide, releasing a highly reactive atomic oxygen atom. That atom immediately bumps into regular O2 and forms ozone, right at street level.
Along with a whole host of other secondary pollutants like PAN, which causes severe eye irritation.
So how do I explain this contradiction to a student without sounding like a total cliche? I mean, in the stratosphere, we globally banned chemicals to protect the ozone layer because it saves us from cancer.
Right.
But down here in the troposphere, ozone is destroying automobile tires and damaging human lungs. It seems contradictory.
Well, I'd say avoid the cliche of calling it a Jekyll and Hyde molecule. Instead, compare it to something really visceral like water.
Water.
Yeah. Water in a glass is essential for survival. Water in your lungs is lethal.
Oh, wow.
The molecule itself, H2O, hasn't changed at all. Its biological impact is entirely dependent on its location. And the exact same is true for O3.
That makes perfect sense.
Right. In the stratosphere, its capacity to absorb high-energy UV radiation provides a necessary shield. But in the troposphere, you are directly exposing delicate biological tissue to a really potent oxidizing agent. In chemistry, context is absolutely everything.
That is a fantastic pedagogical tool. Water in a glass versus water in your lungs. It completely demystifies the contradiction.
I'm glad you like it.
Okay, let's take this chemistry completely indoors now. Because we usually associate pollution with massive industrial scale, smoggy cityscapes or coal plants. But the chemistry inside our own homes gets surprisingly intimate.
It does.
Yeah.
Indoor air quality is heavily impacted by the materials we use to build our environments. Carbon monoxide, CO, is perhaps the most famous threat, right? Often resulting from faulty furnaces or just poor ventilation.
Right, and we all know we need detectors. But the textbook explanation for its lethality is actually really striking. Why does a simple molecule of carbon and oxygen kill us so quickly?
It is a molecular competition that oxygen simply cannot win.
How so?
Well, both oxygen and carbon monoxide are capable of binding to the iron ion at the center of your hemoglobin molecules in your blood. However, the physical and electronic structure of carbon monoxide gives it an affinity for that iron that is approximately 200 times greater than that of oxygen.
Wait, 200 times?
Yeah, about 200.
So it's not just crowding out the oxygen, it's aggressively locking onto the hemoglobin and just refusing to let go.
Exactly. It forms a highly stable complex called carboxyhemoglobin. And once that happens, that hemoglobin molecule is permanently disabled. It can no longer transport oxygen to your cells. So you are effectively suffocating from the inside out, regardless of how much oxygen is actually in the room.
That is terrifying.
It is.
We also see formaldehyde slowly off-gassing from plywood resins and foams. But the thread that really jumped out to me in this chapter is radon.
Ah, radon.
Yeah, radon is a radioactive gas produced by the slow decay of uranium-238 that's naturally present in bedrock and soil. It seeps through foundations into basements and accounts for over half of all background radiation humans experience.
And it has a relatively short half-life of about 3.8 days, making its decay quite rapid once it's in your environment.
Now, if I'm a student in your general chemistry class, I'm definitely raising my hand right now.
Okay, what's the question?
The periodic table clearly lists radon in group 8A. It's a noble gas. We've been taught that noble gases have full valence electron shells and are completely unreactive and safe. So why is a noble gas causing lung cancer?
And see, that is the perfect question. It gives you a chance to draw a hard line between two distinct domains of physical science. chemical stability versus nuclear stability.
Okay, let's break that down for the lecture.
Sure. So the student is absolutely correct about radon's chemical properties. It has a completely full valence electron shell. It has no desire to share, steal, or give up electrons at all.
Right.
Therefore, it does not form chemical bonds. That is chemical stability. When you inhale radon, it does not react with your lung tissue to form an acid or a toxin or anything like that.
So the electron shell is completely peaceful.
Exactly. The danger lies deeper. In the nucleus, the protons and neutrons bound together at the center of the atom. Radon's nucleus is highly unstable. It literally cannot hold itself together.
Yeah.
So it spontaneously undergoes radioactive decay, shooting off a really high-energy alpha particle. And that is nuclear instability.
And the alpha particle is what damages the tissue.
Right. It acts like a microscopic cannonball, just tearing through the DNA in your lung cells. So the tragedy of radon is actually a combination of its chemical safety and its nuclear danger.
Because it's chemically inert, your body doesn't recognize it as a threat or try to filter it out.
Exactly. You breathe it deep into your lungs, just like ambient air. But because it has a short half-life, it violently decays while sitting inside your lungs, blasting your tissue with radiation from the inside.
So it's chemically safe, but nuclearly lethal. That is a massive aha moment. The electron shell is just a peaceful decoy for a nucleus that operates like a ticking time bomb.
I love that phrasing. It ensures students truly grasp that the atom is not a single, uniform entity. It has layers of behavior, and understanding the distinction between atomic bonds and nuclear forces is just absolutely crucial.
Look at the incredible teaching journey we've covered today for your 3-term sequence. I mean, we've taken atomic emission spectra and painted them across the sky with the auroras. We've used space shuttle tiles and Antarctic ice to prove that gas reactions desperately want a surface to cling to. We've turned a catalyst into a rogue lockpick in the stratosphere, and we've watched asymmetric trace gases literally dance to the rhythm of infrared heat.
We've also seen how the fundamental properties of elements dictate industrial engineering, right? Like using limestone to force a phase change in power plants, or understanding how a noble gas can bypass our biological defenses.
It's proof that Julia Burge's atoms first approach isn't just, an academic exercise. The invisible quantum rules governing an electron shell are the exact same rules dictating global weather patterns, atmospheric survival, and the very air we breathe in our basements.
The textbook principles are constantly at work, basically balancing and unbalancing the scales of our environment on a massive planetary scale.
And here is a final provocative thought to take back to your classroom in Oregon. We've spent all this time today dissecting how Earth's atmospheric layers perfectly regulate UV radiation, infrared heat, and chemical balance.
Right.
Imagine the sheer, overwhelming complexity of terraforming another planet like Mars. We wouldn't just be planting trees, we would have to manually engineer and maintain every single one of these invisible, interdependent chemical layers from scratch.
Against the relentless violence of outer space.
Exactly. It really makes you appreciate the fragile, invisible machinery we already have. Good luck with your upcoming term, and keep making those complex concepts click.